Albert Einstein was a leading theoretical physicist who lived during the 19th and 20th centuries. As a Nobel Prize winner, one of his most famous breakthroughs was the special theory of relativity, encompassing the equation E equals mc squared, time dilation, and length contraction. In 1905, Albert Einstein published 2 papers on the special theory of relativity. His first article outlined the properties of light and time, which is summarized with the equation mass equals radiation divided by the speed of light squared. Einstein used L to describe the energy given from an object in the form of radiation, but later replaced the variable with E in his second article. There, Einstein rearranged the items in the original equation and simplified it into E equals mc squared. The effects of this breakthrough are astronomical, as it reveals that mass and energy are 2 different forms of the same concept. This was a secret that had eluded scientists for centuries. Einstein, surprised by this discovery, called it both amusing and enticing, and even wondered whether the Lord is laughing at it and has played a trick on it. This theory implies that any object with mass can potentially be converted into energy. For example, if a penny was subjected to extreme temperatures and pressures and converted entirely into energy, it could power the whole country of Portugal for a year. However, considering the requirement of temperatures and pressures greater than those found in the sun, this experiment is highly hypothetical. Einstein further mentioned the effects of time dilation in his 2 publications. The perception of time varies depending on the relative motion of observers. The physicist concluded that time is not an absolute parameter, but rather influenced by factors such as the speed of the object and the gravitational fields acting upon it. For example, astronauts aboard the International Space Station age slightly less than those on Earth because of their high velocities and lower gravitational fields. This reveals that the length of an object changes based on its speed. The faster it moves, the shorter it appears. Scientists define the proper length to be the length of the object measured at rest. For example, the proper length of a 30-centimeter ruler would be 30 centimeters. However, it would seem shorter if it was moving close to the speed of light. Then, assuming it was traveling at the speed of light, the ruler would appear to have no length. Unfortunately, Einstein's groundbreaking theory of relativity was met with significant resistance in the years following its publication. Conflict rooted not only in scientific skepticism, but also in cultural, philosophical, and political tensions. He contradicted both Newtonian mechanics and the British conception of ether. Dismissed by Britain, ignored in France, ridiculed in the United States, and discussed in Germany. Einstein's theory was not a success from the start. Einstein's publication opposed Newtonian mechanics that had formed the backbone of physics for centuries. Newton's laws of motion were considered sacred truths in the scientific community as it successfully explained motion, gravity, and the workings of the cosmos. Einstein's theory merely elaborated on Newtonian physics, allowing scientists to accurately predict the minuscule differences in the cosmos, an example being Mercury's orbit. Beyond Newtonian mechanics, Einstein's work further contradicted the 19th century British conception of the ether, a substance thought to fill space and act as a medium to transmit light. Shattering the classical British worldview, Einstein was resisted in Britain, with many scientists opposing his theory. Meanwhile, in France, the theory was largely ignored until Einstein's visit in 1910, partly due to the scientific establishment's loyalty to French physicists such as Henri Poincaré. Across the Atlantic, the United States ridiculed relativity as impractical and absurd, disconnected from real-world applications. Germany seemed the only country in which Einstein's theory was discussed, criticized, elaborated upon, and defended, according to Stanley Goldberg, a physicist and historian who worked with the federal government on military science and its social repercussions. However, even there, Einstein's Jewish heritage and progressive views made him a target for nationalist and anti-Semitic backlash. Ultimately, after Arthur Eddington's 1919 eclipse expedition provided observational support, did scientists begin to accept both Einstein's special and general theories of relativity. Einstein's special theory of relativity laid the groundwork for the general theory of relativity, which created a plausible explanation for the phenomena which the Newtonian theory of gravity cannot predict. On Earth and generally everywhere in the Milky Way, the gravitational field is, for cosmic terms, weak. Therefore, the gravitational field, and consequently the celestial bodies, can be described using the Newtonian theory of gravity. Only when observed for longer periods of time do celestial bodies stray from the predictions of said theory. For example, Mercury's orbit reveals a minuscule shift from the point closest to the Sun, which Newton's theory of gravity cannot explain. Only in these situations will physicists use the general theory of relativity. This discovery directly influenced the beginning of the field of astrophysics. Einstein's special theory of relativity implies that time travel is possible, as time is not an absolute parameter but rather changeable. Scientists are now seeking to investigate further with the general theory of relativity. If a person stayed near the edge of a black hole, where there is a tremendous amount of gravity, they would experience time much slower than those on Earth. However, current time machine models need a negative mass and thus a negative energy. However, while an electric current can be either positive or negative, none have found an example of a negative mass. The idea of time travel and its uses have also been debated, as paradoxes exist when dealing with time travel. These conflicting thoughts have made time travel a passive project today. Einstein's theories of relativity also influenced art over the 20th century, as writers began creating stories of chronoportation. This subgenre of science fiction peaked in the 1980s, when movies such as The Terminator and Back to the Future were made. Despite its peak in the 20th century, chronoportation is still an active science fiction subgenre today, much like the discovery of nuclear bombs in the mid-1980s. Einstein, however, indirectly contributed to the discovery of the atomic bomb in 1945. His discovery of E equals mc squared explained the energy released from an atomic bomb, albeit it did not sprout the idea. The thought of the atomic bomb originated from German scientists who were able to split a uranium atom in 1938. Einstein learned of the energy released when the fission occurred and its possibility of becoming a nuclear weapon, and thus decided to write to the former U.S. President Franklin Roosevelt of his concerns. His 1939 letter initiated United States efforts to build an atomic bomb, and in 1941, the government launched the Manhattan Project. Einstein was forbidden from working on the Manhattan Project because of his left-leaning political activism, as it was considered a potential security risk. Einstein later stated that had he known that Germans would not succeed in developing an atomic bomb, he would have done nothing. He repeatedly reminded people that he does not consider himself the father of atomic energy, but rather an indirect force for its creation. When he learned the news of the Hiroshima bombing, he said, "Woe is me."